All right, so we're given a linked list and we want to remove the duplicate nodes. So for example, let's say we're given this list, which they use as an example. So we have, the list is assumed to be sorted in ascending order, so we don't have to worry about anything like that. But we pretty much want to remove this node. I mean, we could remove this node or this node, doesn't really matter. We just want this to end up with only a single node with a value of 1. The 2 is fine because there's only one of those. Then remove either this one or this one. So we want it to end up with a list like it shows over here, just 1, 2, 3. So the idea here, and we're going to be using, I think it's called lazy deletion for this. Essentially, the idea is to take the first node of a given value, so the first node with the value 1, and to have this point to the value, or rather the node that is after the last node of that same value. So this is the first node with the value 1. This is the last one with the value 1. We want the first one to now point to this last one's next node. So this 1 still points to this 2, but nothing points to this 1, so it's lazy deletion. Now same with the 3 down here. This is the first one, this is the last one. The last one points to null. We want the first one to then point to that null. This could be a node with a value of 4 or whatever, but in this case it's null. But the process is the same as what we did for 1, right? This no longer points to this next 3, it points here. Now this 3 still points to null. Obviously it's not the same null, it's just null in general. But that's kind of the idea. It's lazy deletion. We don't worry about getting rid of this connection or this connection over here, that linkage, but it doesn't matter. So that's the intuition for the solution. So what we'll do is we'll keep track of like just a basic linked list iteration, to go through the linked list. We'll just do a simple, check. We'll have a linked list node that's keeping track of the current node. We'll call it cur. And we'll just do a while loop as long as this is not null. Pretty much saying we'll go through here, 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 here. Okay, now we get here, this is null, we break out of the loop. And the idea is to find the node of a given value, keep track of the first one. So as long as the value of the current node is equal to the value that we're keeping track of, we'll just keep moving on. As soon as we find one that is a different value, so let's say value is 1, because that's where we'll start. As soon as we get to this node, when this is cur, when this node with a value of 2 is cur, as soon as we get there, we'll say, okay, well, 2 is not equal to our stored value of 1. So let's take our stored node, which we'll call, I believe, first, because it's the first node of a given value. Let's point first to this node. And then once we do that, we'll set this new node as current. We'll set it as, or rather, no, this is already current. We'll set it as first, the first value with this, or the first node with this new value. And then we'll set value to the value of this node, and then we'll repeat the process. So the code looks something like this. So first off, because the constraints of the problem, they say the number of nodes in the list is from 0 to 300, so it's pretty much saying you could have an empty list. So let's just take care of that corner case first. So if head is null, we'll just return null, because there's no way to modify a list that doesn't exist, so we'll just return null. And then we'll have our cur, which will just kind of be our pointer to the current node that we're looking at. And we'll start that at head, obviously, because it's the first node of the list. We'll also have a list node called first, which is just the first node of a given value, which will start as cur. This could also be head, obviously it's the same node, but. And then we'll keep track of the value of the current set of nodes that we're looking at, right? And over here, when we're looking at all the ones, we pretty much are keeping track. We start at this one, the first one with the value of 1. We're going until we find one right here that is no longer a 1. So that's why we keep track of the value. So we'll start that as first val, and then we'll do our basic, linked list iteration while cur is not null. So the main thing we're really looking for, is when the value of the current node is not equal to the value of the node that we're working with, right? So if we're starting out, let me try to clear some of this up. If we're at the beginning, our value is going to be 1, right? And we're going to be going, we don't care. There could be 100 nodes with 1, with the value of 1 in between, right? They could be 1, it could be 100, it doesn't matter. We don't care about any of those. We care about the first one, which we've already found, and we care about the next node that has a different value. So we're just going to keep going, and that's why our conditional, which I haven't written yet, is has a not equals, right? We don't care about when it equals the same value because there's nothing special to be done there. We only care about when the current node does not equal the value of the first node that we're working with, if that makes sense. So when this happens, what we'll do is we'll say, okay, so let's in this case say this is first, right? Because it's the first node with the value of 1. We'll say first.next equals current, which in this case would be the next node with a different value. So we'll say first.next will now point to current, right? So we removed the connection from this first node to any other node that has the same value, which is a kind of a lazy way of getting rid of duplicates. And then you'd say value equals current.val, because now that we're done with ones, we want to use 2 as the value to be searching for. And then we'll say first equals current, again, because we're done with 1. Now the node that we're going to want to repoint somewhere is now the current node that we're working with, which in this case would be the node with the value of 2 now. And then in every case, regardless of if the current node's value is different from the one we're looking for, in every case we're going to just want to increment current. And then at the end, once we get to the end here, this will still be pointing to this, right? Because we'll get to the point where current is right here. So this doesn't solve a problem. We still have duplicates, right? Because this 3 still points to this 3. So what we'll want to do is just after we break from the loop, we'll just want to point this to null. So that'll be our first node. That's what it'll be stored in. We just say first.next equals null. And then we'll return head, because the way this solution works is head, because it's the first node in the list, it's also going to be the first node of the lowest value, right? In this case, 1. So head will never be modified. We won't lose track of the head node. So we can just return head and know that everything after it has now been modified in a way that solves the problem. And this solution is, the time complexity is big O of n, because we're just iterating through the entire linked list. Like we start from head, right? We start from head and we go until it's null. So if we go from here, right here, all the way to its null. So you're always iterating through the entire list. And of course, in the worst case scenario, because you're doing the same thing, it's gonna be big O of n. Space, I believe, is constant. Yeah, because we're using no data structures. We're just using a cur first value, and that's it. So that'd be constant space.